State space search. This structure is usually used for IIR filter. In this structure, the outputs of the delays are considered as the states of the system. When all the values of external signals and states are known, the future values of system states, delayed inputs, and the system output signals can be determined. Consider the following difference equation for an IIR filter. Without reading the nature of the equation, B0, B1, B2, B3, minus A1, minus A2, minus A3. According to the structure of the direct form 2, the auxiliary variable Wn is defined as follows. Wn is equal to x of n minus A1 times Wn minus 1 minus A2 Wn minus 2 minus A3 Wn minus 3, and Yn is equal to B0 Wn plus B1 Wn minus 1 plus B2 Wn minus 2 plus B3 Wn minus 3. Assuming state 1, S1 being equal to Wn minus 1 and S2 being equal to Wn minus 2 and S3 of n being equal to Wn minus 3, it's observed that Sk of n is the signal at the output of the delay lines. Okay? The input S1 of n plus 1, Wn is equal to that one, B0 output. Delay S1 of n minus A1 plus B1, delay S2 of n minus A2 plus B2, another delay, and blah blah. As a result, S1 of n plus 1 is equal to x of n minus A1, S1 of n minus A2, S2 of n minus A3, S3 of n. S2 of n plus 1 is equal to S1 of n, S3 of n plus 1 is equal to S2 of n. Here you see the regulation. And what about the output? Y of n is equal to B0 x of n plus B1 minus B0 times A1 multiplied by S1 of n plus B2 minus B0 A2 times S2 of n plus B3 minus B0 A3 times S3 of n. In summary, it can be written that S1, S2, S3 all n plus 1 is equal to minus A1 minus A2 minus A3 in the first row, 1 0 0 second row, 0 1 0, and you may guess another rows, times S1 S2 S3 plus 1 0 0 times x of n, and y of n will be equal to C1 C2 C3 times S1 S2 S3 based on the states plus B0 times x of n, where Ck is equal to Bk minus B0 times Ak, and K between 1 and 3. The matrix form, here you see the structure, okay? Is S of n plus 1 is equal to capital A times S of n plus capital B times x of n, and y of n is equal to capital C times S of n plus D multiplied by x of n, where S of n is the vector of state variables with dimensions of n times 1, x of n is the input, and y of n is the output, both scalar. The dimensions of A, state transformation matrix, B input transformation matrix, C output transformation matrix, and D direct matrix are equal to n times n, n times 1, 1 times n, and 1 times 1 respectively. It can be seen that D is a scalar based on the current and previous values of the input and also the value of the system state at the zero moment. The state of the system S of n and the output y of n at the moment n is equal to S of 1 is equal to A times S of 0 plus B times X of 0. S2 is equal to A times S1 plus BX1, which is equal to A times S0 plus AB times X of 0 plus B times X of 1, and S of k will be equal to A to the power of k times S of 0 plus summation from j from 0 up to k minus 1, A to the power of k minus 1 minus j multiplied by B times X of j. And y of 0 is equal to c times S of 0 plus D times X of 0. Hopefully they should be 0. Initial rest. Okay? Y of n is equal to c times S of 1 plus D times X of 1. And you see what it will be equal to. And y of n is equal to c times A to the power of k times S of 0 plus c times summation j from 0 up to n minus 1, A to the power of n minus 1 minus j times capital B times X of j plus D multiplied by X of n. That's it. So the impulse response is equal to h of n is equal to D for n being equal to 0. Otherwise, it will be equal to capital C times A to the power of A minus 1 times B. The transfer function of this system will be as follows. Okay? The first line for u, the second line for u. The third line, h of z, will be equal to y of z over x of z, which will be equal to capital C times z identity matrix minus A all to the power of minus 1 times B plus D, where I is the identity matrix with dimensions n times n. That is, all of its elements are equal to 0 except for the elements of the main diameter, which are equal all to 1. Okay? The poles of h of z are the eigenvalues of matrix A, which are represented by lambda k. The denominator of the fraction of the transfer function is also equal to the determinant zi minus a. If abs of lambda k is less than 1, the filter will be stable. If the coefficients of this structure are changed into a hat being equal to p to the power of minus 1 times a times p, and b hat p inverse times b, and c hat c times p, and d hat d, the transfer function remains unchanged because h hat of z will be equal to c times p times zi minus p inverse times a times p all to the power of minus 1 multiplied by p inverse times b plus d, which is equivalent to h of z. Okay? Where p is a matrix with an arbitrary anti-zero determinant and dimensions of n times n. Another name is similarity transformation. This shows the advantage of the above structure against the changes, of course little changes of the coefficients, compared to the structure of the direct form 1 or 2, because h hat of z is equal, excuse me, h hat of z is equal to h of z. On the other hand, realization of the transfer function with coefficients a, b, c, d requires n plus 1 squared multiplications, which is unacceptable for large values of n. Like other structures, it's better to use only second-order filters in cascade or series or parallel structure, which will be later explained. Now, realization of parallel structure for IIR filter. For IIR filter with the degree of n, h of z is equal to summation k from 0 up to capital M bkz minus k over 1 plus sigma k from 0 up to capital N ak times z minus k, which is equal to c0 plus blah blah plus cm minus n times z to the power of a minus m plus sigma k from 0 up to capital N dk over 1 minus pk times z minus 1. For practical filters, m should be less than or at most equal to capital N, and as a result, only the coefficient c0 can be non-zero, okay? Not equal to 0, and the rest of the ck's will be equal to 0. Also, if a complex pole pk, dk is also complex, and for the filter to be real in time domain, the pole pk star and dk star exist. Complex conjugate. These terms can be combined as follows without reading, okay? If the number of real poles is equal to n1 and the number of complex poles is equal to 2 times n2, then n will be equal to n1 plus 2 n2. The transfer function is also summarized as follows without reading, okay? Where k is between 1 and n, and the real numbers ek and fk depend on dk and pk. Okay. Meanwhile, it's possible to implement each of the first and second degree sections according to one of the four structures of direct form 1, 2, and their transposes, as explained earlier. The constant C0 is also a simple multiplication. The resulting structure is called a parallel realization, an example of which is given in figure 9.13. C0 from input to the output, and here the inner branch, okay? The number of delay lines in the parallel structure is the same as for the direct one. If m is equal to n, even the number of multiplications and additions required for both structures is equal. If m is less than n, the number of additions and multiplications required for the direct structure is equal to m plus n plus 1, while this number for the parallel structure is equal to 2n plus 1 operations for each section. This means that the direct structure will be cost-effective. The only advantage of the parallel structure is the lower sensitivity of its frequency response to the limited word length, which will be discussed in the future sections. Okay. Now, realization of cascade structure for IIR filters. Let the degree of the numerator and denominator of the IIR filter be equal to m. The transfer function will be h of z is equal to c0 times product from k from 1 up to n, 1 minus zk times z minus 1 over products of k from 1 up to n, 1 minus pkz minus 1, zeros and poles of the system. Also, suppose n is even. As a result, the transfer function can be simplified as follows without reading. You see product of what appears here. Okay? With this description, the coefficients of fk and ek will be real. Since capital N is assumed to be even, the number of true poles and zeros will also be even, which can also be written in pairs and summarized in equation 9.36. If n is odd, the above form should be changed. Okay. The first part, cascade, the second part. Okay? Very simple structure. It is called cascade or series realization, an example of which is shown in figure 9.14. Finite precision. So far, we have assumed in the designs that all computed variables and all arithmetic operations can be presented with unlimited precision. In practice, this is not the case and the numbers can only be represented with limited accuracy. Therefore, because a computer word has a limited number of bits, arithmetic operations will be with errors. The act of presenting a number with limited accuracy is called quantization. To illustrate such problems, consider the following digital filter. Y of n plus a1 times a1 y n of n minus 1 is equal to b0 times x of n plus b1 times x of n minus 1. When implementing this filter, the following issues should be considered. The input signal x of n may be obtained by transforming the continuous time signal x of t. As a result, the number of bits of the analog to digital converter determines the amount of quantization error. Fixed coefficients a1, b0, b1 will be accompanied by errors due to the limited number of bits presented in the computer. Therefore, the implemented filter will be different from the desired one, that is, the location of the poles and zeros of the real filter will be different from those of the desired filter. And as a result, the frequency response of the practical filter will also be different from the desired frequency response. The system may even become unstable due to the movement of the pole close to the unit circle, to the outside of the unit circle. Okay? The number of bits required to perform the multiplication operation of a1 times y of n minus 1 is equal to the sum of the number of bits of a1 and y of n minus 1. To solve this problem, if we increase the number of bits required for y of n and quantize the product of a1 times y of n minus 1 with this increased number of bits, it will be an incorrect work. So what's the solution? What should we do? Such an operation leads to an error for each update of y of n over time. If the number of bits required to present x of n and y of n are equal, then the product of the multipliers of b0 times x of n and b1 times x of n minus 1 need to be quantized for each computation. So it's possible, for example, to present y of n with double precision. The range of the values of y of n for presentation with fixed point is limited by the length of the word. Large input values may cause overflow in the output. To avoid overflow, it may be necessary to limit the range of the input signal. Of course, this work has a negative effect. The number of important bits for presenting the signal is reduced by this process, and as a result, the SNR is reduced. If the output of the filter is to be fed into a DAC, it may sometimes be necessary to re-quantize the output to match the number of bits in the converter. This means that yet another source of error must be imposed.